It is my pleasure and privilege to introduce today's esteemed speaker, Dr. Ravindra Jilte, currently serving at Maulana Azad National Institute of Technology, Bhopal. Sir is distinguished academician and researcher in the domain of renewable energy, thermal science, hydrogen technology, and advanced energy system. His work span across the hydrogen production, energy storage, sustainable fuel technologies, heat transfer enhancement, and several cutting-edge development in the clean energy solutions. He has contributed significantly through high-impact publications, sponsored research projects, and collaboration with leading institutions and industries. His deep expertise and research-driven insight make him the valuable resource in the growing field of hydrogen energy and sustainable technology. Today's session will provide us enriching the understanding of the latest advancement, challenges, and opportunities in this evolving area of the clean energy. On behalf of the Mechanical Engineering Department AIT, we are honored to have Dr. Ravindra Jilte with us today. Welcome, sir, for your session.
Thank you, sir. Am I audible?
Yes, sir. Yes, sir. You are audible.
So shall I start, sir?
Yeah, sure, sir.
So respected head of the department of AIT, all key members of organizing team, and dear participant. Today we'll be discussing and attending on a session called as hydrogen production using modified solar reactor from two-step water splitting CeO2 cerium oxide based thermochemical cycle. Uh, as Sir has introduced, the FDP is on hydrogen 360-degree, unlocking the potential of sustainable power. So we all are aware of producing the hydrogen from electrolysis. But there are so many other options are available for generating the hydrogen and meeting our demand. So I will be discussing on one such method called as thermochemical way of generating the hydrogen, and that too from two-step water splitting cycle. So before we begin with the actual topic, let us have some kind of background why we want the hydrogen and what are the requirements of the hydrogens from the different sectors. So if you look at the global hydrogen consumption over here, we can find over here almost 55 to 60% of the hydrogen is required for the ammonia production. Then the second one is about the petroleum refinery. It also required 25%. Now in a petroleum refining, we also need this hydrogen to reduce the content, that is the content of the petroleum to the diesel and petrol, as well as to carry out the filtration. The sizable amount, like 10% of the hydrogen, is also required for methanol production. And now the era is there where we are switching to the electric vehicles. Also, we are switching to the hydrogen fueled car. So if you look at the hydrogen fuel car in terms of fuel cell, that also demands almost 10%. So these are the at present the global hydrogen consumption by the industry. If you again look at the, like for example, the ammonia production, which is 55 to 60%. So it has got the other so many applications wherein you will find out its uses. For example, majority of the ammonia, we know that it is used for fertilizers. But apart from that, there are so many products are there, so many activities are there, and so many industries are there that requires the ammonia. Like for example, if there is a pulp and paper industry is there, or food production is there, water purification is there, refrigeration is there, cleaning products are there. So all the uses of ammonia I have not displayed and listed over here, but at this point we have to understand that the basic the way of producing the ammonia is the hydrogen, and our topic itself is the uses of the hydrogen, how to generate the hydrogen from sustainable way. The second 10% of the hydrogen also required for methanol, and the methanol consumptions, we can say there are so many, like to produce the acetic acids are there, distillates are there, ethanol are there, or DME is there, and so many other applications are there. So this will just briefly give you the idea that there are requirements of the hydrogen by the industry. And industry is not the single industry like the petroleum. It has got the wide varieties of the industries. So now if you again go through the at present, so we can classify the hydrogen the way it gets produced. Like here, majority of the hydrogen which is at present required by this industry, we call it as gray hydrogen. And it is produced by simply steam reforming of the methane or something. We call it as SMR. It is a gray hydrogen, but at present we are fulfilling the need of the industry. Maybe we are compromising on the pollution point of view, or maybe we are uh, compromising on the environmental damages which is occurring by gray hydrogen. But the demand is there, so we cannot stop the industrialization. We cannot stop the growth of the civilization, civil society or something. So needs are there. So at present, majority of the hydrogen comes from the gray hydrogen. So if you look at the and the topic and the FDP is about the green hydrogen, and that too it should come from the sustainable. So there has to be the clear pictures about gray hydrogen, blue hydrogen, and the green hydrogen. Like gray hydrogen, we take the the natural gas, or we can take the CH4. We can carry out the reforming of the CH4, but hydrogen can be produced, but at a cost of liberating the CO2. So if this liberated CO2 or the carbon dioxide, if it is not get captured or sequestered, then this is called as a gray hydrogen. And in the second method, we also have the, since the constraints are there and so many international the constraints are there, and the we have to follow certain conditions, like you cannot liberate the carbon dioxide to the atmosphere freely. So in second attempt, we still use the reforming of the CH4 to produce the hydrogen, but we have the all the carbon capture storage methods over there, which we try to install in a plant. And then once the carbon dioxide get captured, we try to store it to a place where it will unaffect the environmental damage or something. So in underground storage or underground the sea or the oceans, we have found out the abundant kind of, or we have the so many kind of the reservoirs are there, empty kind of things, where we can put this CO2. So that is the one way of doing it. This is the blue hydrogen. But here, for converting from natural gas to the hydrogen, we require the fossil fuel. So here the fossil fuel is there. Now, if you try to replace this fossil fuel with the renewable, then it is called as a green hydrogen. So in case of the green hydrogen, we'll try to carry out the electrolysis of the water. And once the electrolysis of the water carried out, we get the hydrogen. As a part of it, we get the oxygen. But for the electrolysis is the intensive, energy intensive kind of process is there, wherein it requires the electricity. So this electricity, if you can provide by the sustainable way or by the green way, for example, the PV plant can be utilized to provide the electricity. So that concept is called as green hydrogen. So electrolysis as such is the what you can say the mature kind of technology is there, although the research is still ongoing. But the topic which we have taken for the presentation in today's FDP is something different. Rather than following the electrolysis of the water, we are trying to find out the thermochemical way. Uh, so many options and methods are available to produce this hydrogen. As I said, if you utilize the solar, if you install the solar photovoltaic panels, solar electricity, if it is utilized for electrolysis of water, you can get the hydrogen, again called as green hydrogen. You can also carry out the photolytic splitting of the water, again hydrogen. Then you can utilize the wind energy also, because what is required is the electricity. So electricity we required from the renewable sector. So whether it is from the solar or the wind or any of the sector is there, we call it as the blue hydrogen, sorry, green hydrogen. The another way is the biomass, wherein we can carry out the fermentation and we adopt the biological processes. Then there is another method called as the thermochemical way of converting, and this is the topic for our discussion. So in our case, what we can expect in our discussion is the solar will be part of the discussion, then thermochemical method will be the part of discussion, and we majorly will be discussing on thermal splitting of water. So this will be our part of discussion. But at present, there are so many other methods are also available. For example, through the natural gas, you can carry out the pyrolysis, you can carry out the steam reforming, plasma reforming, or from the partial oxidation. So ways are available to produce the hydrogen. Out of this conversion methods, few methods are there which we can say at present reach to the mature level, and few of the methods, for example, thermal splitting of the water, is at under development kind of at research level something, wherein efficiency is less. So there is a scope for the research. So normally we try to conduct the FDP and we try to deliver a topic wherein the research opportunities are possible. So this is the one way of having this topic for the discussion. Then the concepts called as the solar fuels. Now the solar fuels is basically what we are saying is, suppose say if the diesel is not available, or we can say the kerosene is not available, or then how will you fly the aeroplane and all other activity? So can you produce the jet fuel artificially in the laboratory? That is what the happening over there, because many of the activity deals with the diesel engine, or it deals with the kerosene, or deals with the petrol, or so many other things are there. So what we try to do over here, the research over there, if you can provide, or if you can produce some kind of the hydrogen in a laboratory condition, which is happening over there, or some kind of syn gas, which is the mixture of CO plus H2 is there, then under certain process, we can pass this syn gas to produce synthetic kind of diesel, or synthetic kind of kerosene, or synthetic kind of fuels. That fuels, since we are utilizing the solar heat to carry out these processes for generating the hydrogen, or for generating the splitting of the CO or syngas. Here we are utilizing the solar energy. Since it is the energy intensive process is there, the fuel it will produce, like synthetic diesel is there, it is called as the solar fuel. So for a solar fuel, we have the cycle like, and the very important thing for the solar fuel is we try to utilize the natural available resources which is abundant in the nature, like water is there, or the carbon dioxide is there, the nitrogen is there. And then we try to utilize the solar heat. We try to produce the hydrogen, hydrocarbons, ammonia, that is energy rich chemicals. We try to utilize the multiple of the activity, like electricity is one part, heat is also one part, and this is what the uses. Apart from that, the solar fuel, as I said, is also targeted for the jet fuels or other applications. So this is the just brief about the solar fuels, and methods are available for solar fuels, like we can utilize the solar heat, and in a solar heat we can include the reactions which is of photochemical, photobiological, electrochemical, or thermochemical. And in today's class, sorry, in today's FDP, we are discussing on the thermochemical part. And the best part of this, the solar fuel is that we can use the existing kind of the infrastructures, And since the FDP topic itself is on a sustainable concepts, so solar fuels are sustainable, produce no net emission of carbon dioxide. This is what the advantages of going for the solar fuels. Now let us look at the solar thermochemical processes. So we can carry out solar thermochemical process in a one step, in a two step, or a multi-step. We'll discuss what is the basic advantages between the one stage or drawbacks of having the entire reactions to be in one step, and why we are going for the at least two step as per the topic. But what is required over here is we require only the raw material as the water. Here we require, like here I mentioned, we only require the water, we only require the solar heat, and then we are able to produce the hydrogen. Now this STCC is called as the thermochemical conversion. Uh, Now the since the solar energy will be utilized or solar heat will be utilized, but briefly if you look at the basic structure will involve the concentrator kind of arrangement will be there, because single flat plate kind of the collector will not able to generate the electricity which is required to carry out these reactions. So what we expect? We expect some kind of solar technology will be involved in a system. Then the concentrated kind of radiation will be subjected to the thermochemical reactor. Now in the reactor, some kind of reactions will occur, which we'll be discussing later on, and we'll able to collect the hydrogen, which is the purpose of carrying out this. So here reactants, which at present is the cerium oxide, are exposed to the high temperature to split the water molecules into the hydrogen and oxygen molecules. We'll see later on how to achieve this or how to carry out this, and what are the opportunities are available at our level to further experiments or further carry out the research. But here, as the number of steps in a solar thermochemical cycle increases, the required operating temperature decreases. So, before we delve into the topic, the classifications of thermochemical processes will discuss. In all the cases, we'll be utilizing the concentrated solar energy. Multiple of the options are available. We can take the water, we can split it by thermochemical process by applying the heat, or you can take the water, carry out some kind of solar thermochemical reactions by using some cycles. We can also carry out the solar reforming, like we have the steam reforming or the methane reforming, produce the solar hydrogen. We can also take the solar heat, and then we can try to carry out the solar cracking of the fuels, like the natural gas is there, oil is there, coal is there. So solar cracking is also possible. And lastly, we have the options of carrying out the solar gasification. But as I mentioned that we'll be discussing only on one pathway. So before we discuss on this part, what is required, we require the concentrated energy. So we'll try to just review that there are so many options of producing the concentrated heat. Mostly we'll try to utilize over here the parabolic dish kind of concentrator or heliostat kind of concentrator where high temperature is possible. Among this, the parabolic trough collectors are available, or you have got the heliostat tower arrangement is there, or you have got the CPC kind of collectors or receivers are available, and then you have got the parabolic dish. So we'll be utilizing the systems where the concentration ratio is higher. So it depends on the concentration ratio. Now, here little bit understanding is required because in our case, when we try to carry out the reactions, two step is there. We'll discuss. So certain temperature is required for one strip and the another level of temperature is required for the second strip. So we'll have to adjust our concentration ratio, or at least we have to design the solar thermochemical reactors keeping in mind that temperature. So we should also know what is the concentration ratio and what concentration ratio is required to generate that level of the temperature. So I hope you have enough of the idea about the concentration ratio. So at present, I am just uh, specifying the concept over here. So if I take the concentration ratio over here, which will be a part of discussion and utilization in our the upcoming slides over there. We take this particular area, like this is the area is available, and this is the area is available on which the radiation will fall. So this area we call it as a aperture area. So or a dish area. So aperture area means through which the solar radiation can enter. So these are the entire area is available. So this area, if you take it, so let us say my aperture area is available somewhere here, and this is the receiver area on which all the concentrated radiation will fall. So this area is supposed to say called as the receiver area. So if you look at this, this area is almost 100 times bigger than this area. So your concentration ratio will be 100. So in a typical situation, if my radiation is about the 800 watt per meter square, so it will becomes 100 into 800 watt per meter square. What I am doing, I am simply trying to concentrate the radiation to a smaller area so that the intensity will get increased based on concentration ratio. So higher the concentration ratio, higher will be the temperature that can be developed for a given system. Typically, the solar towers can be in the range of a 300 concentration 300 to 1500, and the temperature can be up to 1500 Kelvin. If you take this solar dish arrangements, then concentration ratio can be in the range of 1000 to 5000, and temperature can be in the range of 1800 Kelvin to 2000 Kelvin. So higher temperature is possible in case of the solar parabolic dish systems as well as the solar tower system, which is displayed on the screen. Then the solar thermochemical processes, as I mentioned in the previous classifications, uh, we'll be utilizing in our discussion solar thermochemical process wherein we'll be utilizing the metal oxides, like the cerium oxide is available, and that too we'll be discussing on a non-volatile metal oxides. In non-volatile metal oxides, our discussion will be purely on a Syria-based redox reaction. So these are the pathway of our discussion for today's FDP. Although there are, as I mentioned, other options of producing the hydrogen as well as the syngas. Now, although the topic is only about the generating the hydrogen or producing the hydrogen in a sustainable manner, but since we are also discussing on a solar fuels, the syngas forms or utilizes there to produce the solar fuels. These are the common pathways available. So first process, if you look at the thermolysis. Now, why this is required to be discussed over there? Because we have got the equivalent of the process called as the electrolysis. So if you provide the electricity, you call it as electrolysis, and if you provide the thermal heat, equivalently, if you provide the solar heat, we can call it as a solar thermolysis. Now the question is that electrolysis of the water for producing hydrogen is almost utilized nowadays, but solar thermolysis is not popular. So what's the reason or there? I mean, somebody may be thinking that simply trying to provide the heat by the solar and try to split it. But here it is the idea. The concepts of solar thermolysis is to dissociate hydrogen molecules to produce hydrogen by supplying solar heat. But it demands very high operational temperature temperature up to the range of 4300 Kelvin is required for the water dissociation. Since we have got the technology, as we just now discussed, wherein we have limited by the temperature, like 2000 Kelvin or in the range of 1800 or something. If it is the case, then whatever the solar heat is available or will be available will not be sufficient to generate that much temperature. So we have dropped this idea of producing the hydrogen by the solar thermolysis. So this is the one drawback we can say. Then another question is there. Solar thermochemical cycles are used to counter the two problems related to the thermolysis. That is to take care of the two problems which is inherent in case of solar thermolysis. First one is in case of the such as separation of the hydrogen and oxygen molecules which might formulate explosive, and so the separation of the hydrogen and the oxygen is the requirement. So that is taken care by the thermochemical cycles. First case. Second case is the requirement of the high temperature is also taken care by the thermochemical by carrying out that reactions at a lower temperature, which is possible to produce in a conventional, or we can say the at present solar technologies. So solar thermochemical cycles can operate at a relatively low temperature as compared to thermolysis. And while solar thermolysis produces hydrogen and oxygen in a single step, thermochemical cycles produce hydrogen in one step, H2 and O2 in two different cycles. So we have the two different cycles means we have the redox kind of reactions where reduction is one reactions, oxidation is one reactions. And therefore we can get the liberation of the hydrogen over there. Thus there is no challenge in the separation. So that is the advantage of why we are going and discussing on this thermochemical cycles. Then if you look at the at present, what is the status of research or what's the opportunities for us to explore this topic. So many studies have revealed that most of the thermochemical cycles usually functions in the temperature range of 850 to 2200 Kelvin. Question comes, there are almost more than 280 cycles are available, identified by CNRS for the production of hydrogen from the water. And out of these 280 cycles, we are discussing only on one cycle, which is proven to be at present, which is proven to be a good feasible to adopt. So not all the hydrogen production cycle pass the criteria according to the cost, because there are multiple of the things we need to see. Cost factor is there, energy required to carry out the reactions, environmental effect, safety, and thermodynamic aspects. All the things we need to look at. That's why screening is required, because out of these 280 cycles, we need to first carry out the screening of the processes or screening of the cycles, and then we try to find out which cycle is the best. So we have to identify the most suitable cycle for the hydrogen production. So people across the globe, they have carried out detailed analysis on this case, and they have come up with the some of the redox material wherein you can carry out the thermochemical reduction and oxidation, that is redox cycle. So the criteria which we will be utilizing for screening of this the water splitting thermochemical cycles. First, the cycle maximum temperature compatibility with the solar concentrating system. As I mentioned, since we have the limited, or we can say we have the upper limit of generating the higher temperature from existing solar concentrating system, keeping in mind the concentration ratio. And this concentration ratio is also comes from the structural point of view, because if you try to make the very large kind of system is there, parabolic dish particularly, we have the constraints. For the heliostat tower kind of arrangements, we do not have this constraint, but still operational point of view, there will be some restrictions. So we will have to first match the compatibility in terms of temperature and availability from the solar systems. Then how many steps are required in a cycles, how many chemical elements involved in the systems, and then we have to carry out the theoretical and the technical feasibility of the cycles. And in the present, this presentations, we have carried out the technical feasibility. We have carried out, I mean, in fact, we have found out the solar to fuel conversion efficiency. And from that efficiency, we can say that the cycle which you have adopted over here out of this more than 200 is feasible. And then we need to carry out this efficiency analysis, the environmental safety analysis. So all these things are required for choosing one cycle or choosing the best cycle for your application. So thermochemical cycles, as I mentioned, can be a two-step, can be a multi-step. And as I mentioned somewhere previously, if you go by the multi-step, the temperature requirement is less, but challenges are there. So in a two-step cycles usually operates higher than 1000 degrees Celsius. And if you go by the multi-step, then the temperature is, you can operate less than 1000 degrees Celsius. This is what they mention over there. Then in our analysis, if you look at the charts which are produced here, non-volatile metal oxides, we have the options of going for the ceria and the ferrite. We have chosen the ceria. Now there should be some reasoning, and the literature background or background is required why you are choosing this area. So here it is the justification, the advantages of having the ceria in our reactions. So this is the case. Ceria, if you look at, it is had the several properties. It makes the good oxygen carrier and the redox material. Like it has got the high oxygen storage capacity and exchange capacity. Ceria can store and exchange a large amount of oxygen. Second, structural stability. Ceria can maintain its crystal structures over a wide range of oxygen non-stoichiometry. Fast kinetics, which is required, has fast kinetics during the redox process. Then Ceria exhibit non-stoichiometry, which means it can release oxygen at higher temperature without changing the phase. Now here, when you talked about the non-volatile kind of systems which I'm mentioning, uh, we we are adapting the process of the reactions where the change of phase is not there. This oxygen is release is reversible, allowing ceria to take the oxygen again at lower temperature. It is a cyclic process, so we need to continuously liberate the oxygen, and again we need to again make the cerium oxide. Thermal stability is very much, we found out stable is there, good choice. And then ceria has got the oxygen ion conductivity. Catalytic property makes it effective in the catalytic process. So we also gone through the other material like ferrites, and we found out that ceria is the best suitable candidate for our research or for our discussion. So we have conducted the research on it. Then let us look at the now the topic we are discussing here. Let us say we have used the ceria because we have found out that not that much peoples and the researchers have explored. Then to utilize this the topic, we require the thermochemical solar reactor. So in a discussion, in a today's discussion, we'll also try to discuss on this majorly how to design and develop this solar thermochemical reactor. And lastly, we'll try to discuss on how to improve the efficiency, solar to fuel efficiency. Uh, so here it is the process. We call the redox reactions occurs in the two step. In a first step, it's called as thermal reduction. It produces the oxygen. So for the thermal reduction, we try to expose cerium oxide under a heat. So it requires the high temperature. So high temperature reduction reactions, we try to establish or dissociate cerium oxide as a turn, it will produce the oxygen, and reduced form of the cerium oxide is available where oxygen is liberated. And now we try to provide the steam. So when you try to provide the steam in a second case, we are trying to, because steam is there, your hydrogen will come from the H2O. So what we do, we try to pass this steam and liberate the hydrogen, but in between we have to carry out reoxidation. That is again the CeO2 2 minus X, which is less on the oxygen, will try to take up this oxygen. So when it try to take up this oxygen, you have the liberation of the hydrogen, which is required. So it produces the hydrogen. Here it is shown over there. So at a low temperature, oxidation reactions, that is the water splitting, we take this reduced cerium oxide, we pass some moles of the steam, and then we have got the CeO2, that is the original cerium oxide, and then we liberate the X mole of the H2. So since we are continuously destabilizing the cerium oxide with the help of heat to the reduced form, and we are continuously generating the uh, hydrogen, and we are converting back to its original material, that is the CeO2. So CO2 will be remain present, or the cerium oxide will be remain present over there. Only thing is it will expose to a different temperature to dissociate on one side and to dissociate on the other side. So it is a cyclic process. Therefore, we call it as a cycle. So reduction occurs when a CO2 or ceria is exposed to the inert atmosphere at around 1500 Celsius or 1600 Celsius, and hydrogen release occurs at 800 degrees Celsius. Now, if you look at it, also says that the reduction process, that is this process, demands the different temperature level, that is 1500 degrees Celsius to 1600 degrees Celsius. For example, here it required 1500 degrees Celsius to 1600 degrees Celsius to carry out this dissociation of the cerium oxide into oxygen and reduced form. And in second step, we require the temperature of 800. Now here it comes the challenge. It comes the challenge as the case because the solar thermochemical reactor will be there, which will be subjected to a different kind of flux condition, because we do not have the other way of generating or other way of providing a different temperatures. We can only cut the portion of the solar radiation in one step or in the second step, we can say. So this all these arrangements are possible practically because we have the options of changing the concentration ratio. That is possible. So crucial part, because this reactions will be carried out in a closed cavity. This cavity will be like, for example, I have the cavity like this. And this material which you are saying cerium oxide, I'm putting over here. This is the material. So I have to protect this from the atmosphere. I can protect it from the atmosphere by providing some kind of the capping or some kind of the insulation or something. But one way or one side should be open for allowing the radiation. But now the constraint is there. If I try to keep it open for radiation entry, the atmospheric air will also try to enter. And the cerium oxide, which is we are keeping over here, will affect. So what we do, we normally try to provide solar thermochemical reactor. So in a solar thermochemical reactor, we try to provide some kind of cords over here to protect this environment. So design of this solar thermochemical reactor itself is the challenging and itself is the research topic. So we have taken that also. So here it is the case. Solar reactor is the crucial part, we can say. The aperture diameter and the cavity shape are two most important factors for the solar to fuel conversion efficiency, which we have carried out. And these two factors will require to balance between them and make process more efficient. So what we have done at present, so far, we try to investigate on a flux distribution in a solar cavity receiver. Initially, we have modified the solar cavity receiver. We have proposed our own shape over there, which we call it as a modified solar cavity receiver. And then we try to investigate on a flux distribution before we invoke this cerium oxide redox reaction. Uh, since we are putting the cerium oxide, we also require thermal characterization and porosity analysis of nanostructured Syria stabilized zirconia. And then we also try to investigate, although we have not done this part, so I'm omitting this part. Oxy-fuel radiant heat source. This is at present we have not explored, but the last part we have carried out. We have performed it analysis and the CO2 based cavity reactors for hydrogen production. We have performance evaluation has been carried out in terms of the efficiency. So methodology which we'll be discussing in this case will be like numerical approach will try to follow to design the solar reactors. For that case, we'll first analyze on a solar flux. Then solar flux will help us in providing the values of temperature distribution in the cavity. As I mentioned, we require the two range of the temperature to carry out the reduction and the oxidation. So that will come from the solar flux. So initially we'll analyze the solar flux, we'll analyze the temperature distribution. Then we also will try to modify the shape of the cavity, the aperture diameter. So that we call it as a geometrical parametric analysis to identifying the best shape for solar thermochemical. This is the, but prior to that, we also try to carry out the characterization, material characterization through the same. So experimentally, the scanning electron microscopy is being used to analyze the zirconia coating on a cavity. And then lastly, we'll try to demonstrate the hydrogen production through numerical techniques. And we also provide a few slides on efficiency analysis. This is what the layout of the presentation also. So the first part, this is what the conceptual design of a solar thermochemical reactor. What we can say, what we can look at over here. We have obtained this shape by combining the cylindrical cavity with a hemispherical cavity. So it's a combination of a this part is your cylindrical and this part is your hemispherical. So combination of this we have proposed. Now in this analysis, as I mentioned, since we have to protect the entire reactions from the atmosphere, quartz, glass, we have put it over here. And here the RPC is there, which is called as the reticulated porous ceramic. That layer of the RPC, like here example, 20 millimeter thickness RPC catalyst thickness we can observe over here. In analysis, we have varied this thickness. So in a analysis, we have taken this RPC thickness of a 15 millimeter, 20 millimeter and 25 millimeter to carry out the analysis. Now this, if you look at the actual photograph of the RPC, uh, we can look at it's a class of open cell foam type ceramic material characterized by the interconnected network of solid ceramic struts and white spaces. And they are highly porous, lightweight, permeable to fluids, making them valuable in wide range of engineering and chemical applications. So the same analysis we have carried out on this part also. So the first analysis we carried out on optical and thermal analysis of a reactor, because we wanted to first find out the uses of that shape and the temperature distribution, flux distribution. So here it is the aspect one. In aspect one, what we'll discuss on solar flux and associated temperature distribution. So what we will obtain? First, we'll try to obtain the solar flux. From the solar flux, we'll try to obtain the temperature distribution. And this temperature distribution inside the RPC or in the RPC zone, because your radiation will come over here, it will try to strike over here, get absorbed. It will come from this side, it will try to absorb in RPC. So what we required enough of the temperature over here. So what is the aim of the study that we carried out? We carried out the effects of flux distribution caused by the shift in the focal point with Monte Carlo ray tracing methods we adopted that we'll discuss in the upcoming slides. We also tried to, because this is the parabolic, if you look at the parabolic dish is available, and here we are trying to put this cavity at the focal point. So in this, because this radiation falls over here, it reflects over here. So this, there can be irregulatory slope errors on this case. For example, rather than getting reflected from this direction to this direction, if it is getting reflected slightly over here. So there can be errors in the surface, because optic analysis is there. So optic analysis basically talked about what is the optics we have used, like the mirrors, concentration systems, associate analysis, that is the optic analysis. Thermal analysis will talk about the temperature distribution and the solar flux. So here the effect of slope errors, its direct influence on the flux magnitude and the profile we have studied. RPC thickness for this analysis, for example, we have kept 20 millimeter, and in our case, we have also the provision of passing the inert gas, like inlet is available. So what we have done, we have also placed this inert gas, sorry, inlet for the inert gas over here. Now this inert gas, like here, inert gas, why it is used in a Syria thermochemical cycle to create the low partial pressure of oxygen, which enhances the reduction of material. Inert gases, we utilize the argon, but nitrogen can be utilized. The most commonly used inert gas is purified argon, which is therefore we have utilized the argon because it is abundant and relatively inexpensive. Now this the inert gas will try to sift out the oxygen which they form. I mean, if you look at the previous case, if I go by the previous reactions over here, in a one process we get the liberation of the oxygen. Now this oxygen has to be taken out of the cavity receiver. So somewhere when this liberation of the oxygen is there, the reduction of the CO2 to CO2 2 minus X is there. This oxygen will take from the cavity receiver with the help of inert gas. That is the uses of inert gas also, apart from maintaining the partial pressure. That is what they are mentioning. So typically what we have done, we have used Monte Carlo ray tracing technique. Now you can use your own. I mean, there are so many softwares are available that works on a Monte Carlo ray tracing techniques. One such software, we call it as a salt trace software. We'll discuss that also. So what is the solution algorithm we adapted? We adapted the solution algorithm in two ways, because we wanted to carry out the optical as well as the thermal. Now the thermal aspects we have studied with the help of CFD. So ANSYS CFD we have utilized to carry out the thermal analysis, and optical analysis we have utilized with the help of salt trace software, that is MCRT. So in a MCRT analysis, if you look at, we need to specify the sun shape, the direction, the optical parameters, and we need to obtain the flux distribution. So let us briefly discuss before we delve detail into this thermal analysis or the CFD analysis. But just to have a look over here, uh, Once the solar flux distribution we obtain from here, that will be the input for this thermal analysis. So in a thermal analysis, we have to start interpret the solar flux distribution. We have to analyze and solve the equations, and then once the solution get converged, we can extract the results. But for governing equations which we are trying to converge, we have the mass transfer equation, because it is the heat and mass transfer kind of example is there, where the species transport is there. So we have to utilize the species transport, the module from the CFD. Then we have the momentum equation where source term is required to carry out these reactions. Then we have the energy equations. But in this case, since our case is about the zirconia, or our case is about the ceria, which is the porous, we have to treat energy equations for the porous media separately, for the fluid domain separately. We also require the DO, that is the discrete ordinate radiation model, or P1 approximation. So those who have worked on a radiation models available in a CFD or in ANSYS, they are known to this discrete ordinate model or the P1 approximation or S2S surface to surface model. But we have utilized this, and then we have to solve this RT equations, that is radiative transport equation we need to solve. We need to adjust the terms in the RT equations. And then and then we have to pass it for the analysis. So all these things are involved as a part of the CFD. It is not the simple case of the plug and play kind of CFD analysis. We need to adjust, and we need to utilize over here the user defined functions to input the different parameters. But let us look at over here. I will try to keep it as simple or something. But the Soltres is utilized to carry out this analysis, Monte Carlo, and a little bit about this. So as I mentioned, there are multiple of these softwares are available, but one such software which is freely available from the NREL is the Soltres. You can visit this website. You can download this software for the flux distribution. And we have also done the same thing since it is freely available. Uh, this is required. Some steps are required. So I will give the idea. We need to define the sun shape, the directions. We need to define the input properties, optical properties. For example, in optical property, you can assume the reflectivity of the surface. You can also assume the slope errors. You can also assume that, for example, here, if it is the solar parabolic dish is there, so it is basically the two elements are there. This is the one step is there, and this is the second step is there. So we have to define the system geometry, we have to define the stages, we have to define the components in a stage. For example, in this components, we have the parabolic concentrator. In a second component, we have the receiver, we have the observer tubes are there, we have the Syria. So many things are there, but and then the choices of the rays number to be traced, and we have to extract the results. Uh, we need to define the sun shape and the directions. So in a literature, we have to find out the sun shape can be taken where it for optical simulation. The literature, if you look at over there, the best shape can be based on the angle of solid angle. And here it is the two options are available to provide. Sorry, in the software we have the three options, but this is user defined. So normally we either choose the Gaussian distribution of the sun shape, or we also have the pillbox kind of distribution over there. Analysis, we have created the Gaussian distribution. So these are the steps are there. Then, as I mentioned, this software will also allows us to input the optical property. We normally try to provide the optical property in terms of the emissivity, or in terms of the reflectivity, absorptivity. So all this optical property can be easily fed. Then now let us come back to the discussion now. So I will go back to the case of this. This is our analysis. We wanted to analyze the effect of flux distribution. And this flux distribution is there. Suppose this is the focal point. This is the focal point. If you can place this reactor over here exactly on a focal point, what is the flux distribution? If you try to shift its location to analyze what will be the flux distribution, so that effect we have studied. So for that case, we have taken the two cases which is drawn over here. In one case, we have kept the focal cavity at the focal point. If you look at, this is the focal point and this is the parabolic dish is there. In the one case, we have kept at a focal point, and in a second point, we have kept this the focal point cavity 20 millimeter inside. So this is the two cases, case one and the case two. In both the case, this parabolic dish is having the slope error which varied. So effect of having a different kind of slope errors, either for this case one as well as for the case two, we explored over there. And the discrete ordinate radiation model we analyze. So slope error is the angular difference between the measured surface normal and ideal surface normal of a design surface, and it comes from the optical performance. So here it is the result we obtained from the salt trace, the flux distribution we obtained for the parabolic dish, and we can say that now the question comes validity of the results. So we try to utilize the published studies from Zhang et al. Is there, and we found out that the salt trace radiation, salt trace simulation results which we obtained is matches with the Zhang study as well as the Liz study. So analysis can be further extended to extract or to formulate in terms of the temperature distribution. And this temperature distribution is essential to carry out the redox reaction. And redox reaction is the process or what we adapted for generating the hydrogen. This is the all uh, the connected kind of the discussion what you are discussing over here. So the solar flux distribution we obtain and then we try to analyze if the slope error is 2 milliradian or the 4 mrad, 2 mrad, case 1, case 2, how the flux distribution occurs. So this analysis we have presented and we obtained that when the slope error is 4 mrad, the flux value is higher than case 2 for both the slope errors. Then now the CFD analysis, because CFD analysis will give us the interior of the thermal picture. So we temperature distribution inside the STCR cavity for the slope error is comparatively. So what we have done, whatever the solar flux distribution we obtained, we try to taken as an input. Here we have mentioned the entire pathway is available. So I will go back to that pathway from where we obtained. This is the case. So whatever the solar flux profile we obtained, we try to utilize now CFD analysis. So in a CFD analysis, first we model this thermochemical cavity. This thermochemical cavity is modeled using ANSYS modeler. And then here, and then we obtained the thermal analysis, that is the temperature distribution through CFD. So this is done through the CFD for both the cases. And then we found out that temperature distribution inside the STCR, that is solar thermochemical cavity reactor, of a slope error 4 mrad is comparatively more uniform. Now we wanted to have the more temperature distribution because our reactions demands that all these area which are putting over there should undergo the same temperature exposure. So we wanted to have the first the conformity confirmation from the temperature distribution side. So we analyze this case, and in the second case also we try to compare. Then temperature profile in both the case, this is the cavity receiver. So we wanted to have the temperature distribution on this side also and temperature distribution on this side also. So in a radial direction, we obtain a temperature distribution along the radial direction in a porous media, because this is the RPC we are putting. So in a RPC, as we mentioned, and as we can see over here, we obtain the temperature distribution, and along the radial direction, we found out that it is higher for 2 mrad slope error as compared to 4 mrad slope error. Then in axial direction, temperature distribution, that is what we required. We required both, but here, as I mentioned, our analysis of a or the production of the hydrogen from the water, as I mentioned, in a two-step process. So for a two-step process, we also just now discussed the temperature requirement is one step is different. In the second step, it is different. We wanted to take the water as the input. We wanted to split the water with the help of solar heat rather than electrolysis, conventional electrolysis. We are discussing on a long-term kind of process, because in a typical electrolysis, you utilize the electricity, which is produced either from the wind power or from the solar PV plants. And at present, are issues about the recycling of the solar PV or utilization of the PVs after its end use or something. So that is not the long-term solution. The today's discussion we are carrying out on a long-term solution wherein the entire world researcher looking at. Short-term solutions, we are producing the hydrogen with the help of electrolysis, and we call it as the green hydrogen, but that is not the going to help in the long term. So this is the process why we are adapting. Then in a temperature distribution, we analyze the axial direction also, and we obtain that for MRAD for case when it's the highest temperature, and whatever the temperature we are expecting from 800 to the 1600 or 2000, it is possible to reach, and this is the position in a direction. So if you look at the depth of the cavity, we obtain that at the aperture, the flux distribution is higher, or on a the distribution of the flux makes uh, the difference in the temperature inside the cavity in axial direction also. So this is the then we analyze the cavity length also. So along the cavity length, we have got the temperature distribution, and so all this data which we can look at or which we can observe on a screen is being extracted from the CFD analysis. So our understanding and our exploration towards CFD has to be need to be widened, because it has got the so many kind of opportunities and so many kind of modules are available. Like chemical kinetics is the one such module which normally we do not explore. So we also extracted the flux contours for a different slope errors, uh, which got displayed over here, and it says that uniformly distributed with a 4 mrad slope error. But now the question will comes, why this slope error will be there, since this very large optical sizing is required. Like here, if you take the concentrator, there will be a very large area. Now this large area we cannot make from a single mirror. We'll have the number of mirrors connected together or stick together or something. So there will be some surface error. Surface error as such we cannot eliminate. The second error is when we try to carry out the tracking of the sun, like here. So sun tracking may not be 100% accurate. So in that case, your rays may get deviated from the focal point. So number of issues are there when we try to when you try to analyze the situation. So taking care of the what is happening on an actual level. So we have taken the slope error. Then we also modified. Let us say first we analyze this cavity reactor, which was made up of the cylindrical cavity, as I mentioned, and the hemispherical cavity. We wanted to analyze that. Let us have another options or another exploration wherein the flux distribution, temperature distribution can be more uniform. So we have changed the shape over there. And with this, we obtained the flux distribution. Again, in the second case also, we have taken the two, three options like case one, we have taken the focal point, then we have taken the 10 millimeter inside, then we have taken the 20 millimeter inside, and then we try to carry out this A cavity, which is this cavity, or which is this A cavity with the B cavity. So in a B cavity, the similar kind of exposure we have given. Here is the similar kind of exposure we have given. So in both the case, we obtain the flux distribution. We compared the flux distribution. We also followed the similar kind of, because this results we already obtained. What we have added over here is this B part. The one this result was available previously. We just modified the cavity and we obtained the second set of results, and then we try to compare with a similar kind of errors. So we carry out the analysis. We extracted the again the same thing. As I mentioned, another case was there, which is apart from the temperature extraction on a radial directions and axial direction. Later on, we'll see. We also explored the thickness of the porous RPC, which is in all the analysis, as I mentioned, we have taken here the 20 millimeter or something thickness. That is the thickness of the, here it is the thickness of the, here it is a 20 millimeter. But later on, we also modified this 20 millimeter. In one of the analysis, we also tried to uh, vary the orientation of the inlet, because this inert gas is used to sieve out the oxygen, liberated oxygen. So we wanted to explore that since we are carrying out some reactions to split the water, let us have the change in the orientation also. So what I'm trying to put it over here is that when you try to initiate, when you initiate any of the example or any of the research topic, try to think on possible or the kind of possibility of making it diverse kind of analysis. Like here, as I mentioned, we try to change the shape, we try to change the positioning, we try to change the thickness of the RPC, we try to think the thickness of the inert gas passage. So many things we have explored. So CFD analysis help us in extracting the temperature contours which you have extracted. Now it is up to us because the slices are available. I mean, when you try to take the temperature contours, we try to utilize the terms called as the slices. Now, in all our analysis, although it was very time consuming and the kind of uh, very time intensive kind of simulation is there, we have adapted the 3D modeling only. If you look at this case, we have adapted the 3D modeling. So 3D modeling help us because in a 3D modeling, we can take any slice. Like if I take this slice, I can analyze what is the temperature distribution over here. If I take the one slice over here, I can find out what is the temperature distribution inside of this RPC, inside of RPC from this distance. Or if I take the second slice over here, I can again I can find out what is the temperature distribution over here at a depth of this. So if you try to take the three-dimensional kind of analysis, it helps us in extracting more detailed results. So normally what I do, I mean, we try to adopt 3D modeling, although it is very time consuming and it also required the high-end machines. So that is what constraint is also there, but we try to adopt. So second aspect, as I mentioned, was about the length, axial direction. So in a axial direction, that effect also we have studied uh, the length. So model 1 and model 2 detailed analysis we have extracted, and in our published results, because this results is being published in a journal, we have analyzed and we have also extracted our own understanding, and we try to put it over there as a part of the inference from the graph, what we normally say, or inference from the analysis. So that we have done and present in a paper. Due to the wider kind of audience who have joined this FDP, I will not go much deeper into the what exactly and how we have extracted the things, but our main aim is there are several of methods are available to produce the hydrogen from a renewable way, and there are so many other options and research opportunities are available. So this is what the main theme. Then flux profile, as I mentioned, we obtained the flux profile, and this was done just to achieve the uniform distribution. That is what the required, and the temperature. Then optical errors, as I mentioned, finding. So average fluid temperature in the RPC, that is reticulated porous cerium, we obtained up to 1220 Kelvin and 168 Kelvin for model 1 and model 2, respectively, for 2 emerald 1500 Kelvin and 1510 Kelvin for 4 emerald pseudoferrite. So all this analysis we have carried out through simulation, as I mentioned there, through the simulations only. And we also try to utilize the how the velocity get varied in model 1 as well as model 2. Since internally the area or the volume available to spread these reactions or to expand this reaction differs. We have compared the model 1 and model 2, and we try to present the average fluid flux temperature, which we can say that there is a difference. So shape of the thermochemical cavity reactors as well as the slope affects the fluid phase temperature in a radial direction. In a axial direction, that is, see previously it was the radial direction. We obtained these results and we found out that there is a difference. Similarly, in axial direction also it contributes. So the temperature, the range, if you look at over here, we extracted the, I mean, this we call it as a quantitative analysis. When we try to uh, find out the exact values of the temperature, we call it as a quantitative analysis. And the previous, when we try to represent the results with the help of temperature controls, we call it as a qualitative analysis. So qualitative analysis gives us the brief overview of the solution, but quantitative analysis will give us the detailed analysis. So if you look at the detailed extraction of the temperature we carried out over here, and the influence of the optical errors we carried out. Then if you look at the second case, like here, as I mentioned, this another aspect which we have carried out is the model of transport and chemical kinetics for S2 splitting. So here, this is the typical dimensions which we have utilized for the analysis. Uh, the cylindrical and the arrangement length gives us the 80 millimeter. As I mentioned, 20 millimeter RPC varied from 15 millimeter to 25 millimeter. The uh, the gas flow gap is about 5 millimeter, which is also varied, and this inlet diameter also get varied. So we carried out complete parametric analysis to analyze the situation. So here it is. Transparent quartz glass window is place which allows the solar radiation to enter the cavity. Effect of RPC thickness, the gas flow gap on thermal performance has been investigated. So configuration, if you look at there, if the RPC is 15 millimeter reticulated porous cilia, 20 millimeter and 25 millimeter, whereas the inert gas gap, flow gap is 5 millimeter, 5 millimeter and 5 millimeter. In a second attempt, we have increased the gap. Here it is mentioned, this gap is about gas flow gap. So gas flow gap we have increased from 5 millimeter to 10 millimeter, and we have kept the same variation of RPC thickness 15, RPC of 20, RPC of 25, and we obtained the results on this analysis in a numerical simulation. It also means that we have utilized the CFD. Uh, when you try to present the numerical results, we have to be very sure that your results are no longer depends on the grid. For example, in a typical situation like here, when you try to model this and when you try to mesh this kind of cavity, you can have the X amount of nodes or X amount of the elements there. But if you have the Y amounts of elements, your result should not vary. So what we normally do, that kind of analysis, we call it as a grid independent analysis. So when you have the X amount of grids or X amount of elements over there and Y amounts of elements over there, results should be the same. So you try to vary the number of nodes. Then the second question comes, why this analysis is required? Because when we try to increase the number of nodes over here, your it demands the higher processor. It also demands the higher simulation time. So somewhere we have to compromise. So for that case, you cannot compromise on the results. You can only compromise on the timing, but the result should be the same. So for that case, we carry out the grid independent analysis, which we have done. This is the case that if you increase the number of elements 10 to the power 4 by 10 onwards, your results is same. That is temperature obtained is same. So we have adapted this uh, meshing. The second one is whatever the analysis we are carrying out, whether it is because since it is a numerical kind of analysis, we need to validate the results. So for that case, we have analyzed the safety validation with the help of, as I mentioned, the Zhang study is available. So we have carried out. And as you can see and observe over here, it is more or less close agreement is there between the experimental and present study. Then we also try to validate the another study which is available from the Buffin in terms of the other parameter that is called as the CeO2 reduction validation. So all the three things we have validated. This is about the when we try to increase the flow gap from 5 millimeter to 10 millimeter, how the results got varied. That results are presented over here. Then in the second aspects, the same aspects, we obtain the quantity analysis. This is the quality temperature contours. From that same, we extracted the results and we plotted this the actual values of temperature distributions from all the cases of. And then we also taken the RPC thickness, which we varied. So gap effect, we analyze the in detail. And we have obtained certain kind of conclusions over there. For example, the increasing the thickness of RPC zone combined with the contained gas flow gap leads to a decrease in the average fluid temperature. So there is no meaning of simply putting the more and more RPC. There has to be some optimal thickness of the RPC, which we found out from the analysis. Otherwise, when you try to carry out the redox reactions, there will be incomplete liberation of the or incomplete reduction to the reduced CO2. So all these things we need to analyze before we invoke any kind of reactions. As I mentioned, we also obtained from 15 millimeter to the 20 millimeter of the RPC to the 25 millimeter of the RPC. And whatever the vortex get formed, we obtain on 15 millimeter, which gets dead zone close to the porous, which is obtained over there. So radial radiative transfer path for incident radiation becomes the strongest factor to influence the uniform flux distribution. That is what we uh, inferred from the contours. This is the another results for the 25 millimeter from 15 to 25. The comparison is displayed. This is again, if it is exposed to the like RP zone is exposed to the higher temperature, tends to reach peak values of oxygen concentration. So we taken that 15 millimeter hot upon 20 and 25. So molar fractions contours of the oxygen also we have obtained. Because if you look at and if you just recall from our previous slides, the liberation of the oxygen indirectly gives us the values about the reduction, that is CO2 2 minus X. Solar to fuel efficiency we obtained by the analysis of 15 millimeter, 20 millimeter, and 25 millimeter RPC, and up to 16.18% is we obtained for the case. So now another case, what we have done, as I mentioned, we also wanted to have the positioning and orientation effect. Like here, we are allowing the inert gas to enter by this way, and which is used to swift the oxygen and to create the maintain the partial pressure over there. So if you have the inclination of the inlet, what is the effect? If you have the another inclination of the inlet, what is the effect? Keeping the same RPC thickness, keeping the same inert flow gap. So this we obtained, and 90 degree, 75 degree, and 65 degree. This is the degree only from the horizontal. So 75 degree is there. This is this the subscript got mixed with the numbers, but it is 90 degree, 75 degree, and 65 degree. So this effect we obtained like 65, 75, and 90. We analyze the temperature distribution, fluid phase temperature distribution. For this case, we extracting the results in radial direction also, we extracting the results in the x-z directions, and all these things we have displayed through the CFD analysis. Then we have commented on the uniform temperature distribution for 5 millimeter case, 10 millimeter case, 12 millimeter case, 8 millimeter case, and across the length of the cavity. Then we also have the effect of the RE, that is the values of the velocity or the Reynolds number over there, because we have the options of providing the different flow gas of different velocity. So RE, that is Reynolds number, we varied from over here. We obtain results on a temperature distribution. So effect of fluid velocity, we radial direction, again in axial direction, effect of fluid velocity we obtained, and we try to compare the temperature distribution as a part of the variation in fluid velocity. And then this is the another aspects. We lastly try to uh, take the two cases of reduction, like CO2 got reduced to, earlier we have obtained that CO is there, then 2 minus X is there, because you have the original of CO2 is there. So when you try to carry out the, if it is exposed to solar radiation, in one step we try to liberate the oxygen. So how much is the oxygen is liberated? So if you liberate from 2 to make it as 1.72, or in second case, let us make it as a 1.83. So you are liberating certain fraction of the oxygen. So this analysis we separately carried out for the HSC chemistry software. Since the time constraint is there, I will not be discussing on this particular aspect. But this aspect was also got studied and got analyzed in a situation. Uh, The results just I'm displaying because so many complications are there, which is beyond the scope of in today's presentation. But so many analyses are required to obtain and to conclude on the the results of hydrogen generation, hydrogen production from the thermochemical. So I'll just skip this portion of the last aspects. Uh, I will try to provide that all this analysis has been carried out. We call it as a last aspect, but see, get motivated by looking at this graphs that analysis is required, detailed research is required. And if you look at over there, see, we wanted to compare this case. So solar to fuel efficiency also we obtained by this case as well as for the second case. And this is what the last briefly I just specified. That is same analysis we carried out for zirconia. In addition to that, and this is what the results of the same of a RPC foam structure is available. And these are the all the results which you obtained by this analysis. So this will also gives us the this kind of interpretation. So this interpretation possible, and we publish it in a journal paper. So in light of the time which was given to me up to 7:30, I would like to thank all of you for your participation. If any doubts and errors are there, or sorry, if any queries are there, you may now should be allowed to raise your queries.
Yes, sir. Thanks a lot, sir. It was very nice and researchful scientific session that what we have seen. Any questions from participants? Sir, where we can get the tutorials of salt trace?
Salt trace tutorials are available, but it is not directly available on a
MNREA.
real website.
Yes, yes.
But in some sources, if you try to find out, is available.
Okay, okay, sir.
Yeah, because people have carried out that exercise.
Okay,
Like for example, I have carried out a detailed analysis of this salt trace.
okay.
So in some other FDP or in some others, the kind of
There must be hands-on session that will
yeah.
be helpful for us.
Normally, I conduct the hands-on on a salt race wherein I try to what you can say. We try to discuss on the utilization of our understanding.
Yes, yes.
Yeah,
Yeah. Any question
that is
from
separate
Hello,
kind
participant?
of activities are there.
sir.
Yeah.
Sir.
Yes.
Yeah, good evening, sir.
Yeah, you
I
did.
want to ask, I want to just ask, can you please tell me the link of, share the link of the free software that is useful for the analysis purposes?
Salt race software, as I mentioned, is NREL website is there. And the
Okay,
second software which I utilize is the ANSYS CFD software. If your institute
okay.
is having the licensed version of the ANSYS, you can go ahead with the CFD.
Mm-hmm.
Third software is also available, HSC software, chemistry software. But if you are been into the chemistry side or been into the chemical kinetics, then you can go for that kind of analysis. Otherwise, what I am saying, there are 3, 4 aspects of the research. One aspect is you can have the optical analysis with the salt trace, which is available. Second aspect is the thermal analysis with the help of CFD software, which is nowadays available as a part of institute software like ANSYS. And third one is also available like chemistry software. So all the software may not be required at this point. If you have just entered into the area of this analysis, I will suggest that you just restrict yourself on the CFD, NCs, and the salt trace.
Okay, sir. Thank you so much, sir.
Any other question? Sir, thank you very much for your session.
I would like to thank all the organizers, members of the organization team, head of the department for providing with the opportunity, and dear all the participants for kindly listening to this session.
Thank you, sir. Thank you very much.
So shall we now
Yes, sir. Yes, sir.
take
Yes.
the closer of the session now, and shall we leave now?
Yes, sir. Yes, sir. No.
Okay, thank you once again,
Yeah.
all of you.
Yeah. Thank you, sir. Now we'll wait for 2 minutes.
Hello.
Welcome, sir.
Yeah.
Yeah. Yes, sir.
Am I
Just
audible?
yeah. Yeah. Yes, sir. You are audible. Nice to see you,
Okay.
sir.
Same here.
Yeah. Yeah.
So what is like all people are from India only?
Only India.
Okay. So
And this
why
is
is
AICT sponsored Atal FDB program, all from the India.
okay? But why is it kept at such odd time then 7:30? I thought because you kept it online and at the dinner time of people.
No, no.
Okay.
Okay,
Anyway,
sir. I will introduce you, sir. Okay.
sure.
Now it is my privilege to introduce today's distinguished expert, Dr. Sonal Thengne, who is currently serving as an associate professor in the Department of Hydro and Renewable Energy at the prestigious Indian Institute of Roorkee. Prior to IIT Roorkee, he gained postdoctoral experience about the 4 years at MIT UC Berkeley and Tata Center for Technology and Design in the areas of biomass gasification and torrefaction. Sir is highly respected researcher in the field of renewable energy with a special focus on waste to hydrogen technology, advancement in thermochemical conversion, bioenergy system, reaction engineering, and hydrogen production pathways. His contribution through research publication, innovative project work, and collaboration have significantly shaped the advancement in the sustainable hydrogen technology in India. With deep expertise and practical insight, Sir has been guiding the several ongoing national level projects aimed at transforming the waste resources into a clean hydrogen. So I welcome on behalf of the Mechanical Engineering Department, sir. Now you can share. Sir, you are mute.
Thank you so
Yeah,
much.
yeah,
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 yeah.
yeah.
Thank you so much for the introduction. Just a quick question, like, so all the participants, they are mostly students, or like it's a mix
These
of
are the
student and
faculty
faculty
members.
members?
Faculty members. All are faculty
Oh,
members.
all are faculty members.
Yeah,
Okay,
yeah.
fine. Yeah, so let me share the
Some
screen.
are participating, some are attending. As your question is like that.
Okay, okay,
Yeah,
no
yeah,
worries.
yeah.
So let me just share the screen and please let me know whether it's visible or not.
Yeah, yeah. On the right side, you have the share option, sir.
Yeah, I clicked that, but
You have to
okay.
share the screen.
Yeah,
Yeah,
so my screen is shared, I guess.
yeah, yeah, yes, sir.
PPT is also shared.
Yes, sir. Yes, sir. Now it is visible. Yeah.
Okay, but now I can't see myself or I can't see the participants also. So if something goes wrong or if
No,
audio disconnects,
yeah, yeah.
please
I will
let
do.
me know.
Yeah, yeah, yeah. I will that. Yeah, yeah. No problem.
Okay, okay, thank you. So welcome all of you. I hope you had a nice lectures and sessions in this AICTE approved FDP course. And the topic is really the need of the hour, like hydrogen 360-degree, unlocking the potential of sustainable power. And all of you might be aware about lots of funding going on in the area of hydrogen at national level, at international level. And there is a National Green Hydrogen Mission also, a separate mission dedicated to just hydrogen technology and hydrogen economy. So we are still not sure whether when we would actually see this hydrogen getting commercialized at mass scale in India. So far as electrolysis is concerned, the technology is well advanced. The only thing to make it more green and economical is to find renewable options to like power our grid. And if we could use renewable source electricity to split water into hydrogen and oxygen, I think electrolysis is one of the best technologies to go for. But then once we get pure hydrogen and it's separated from oxygen, storing it for further usage, it's another concern of economics, or it's a cost. So we need to find some like advanced technologies which would help us to store hydrogen at a lower reduced cost. So that's a challenge there. But other than that, since India is a agricultural country, and we are like one of the, I think the world #1 in population. So we have a huge amount of biomass or municipal solid waste at our disposal in our country. And this resource can be utilized for several applications. One of them being hydrogen. Mostly we use biomass or waste for energy applications, or when I say biomass, it's mainly the surplus, residual, or like the extra waste biomass that is there, because the real biomass, we would, like the food crops and all, we would consume it for food and satisfying our hunger. But for energy purpose, we always talk about the biomass which is surplus or which is residual or which comes out as a waste from any of the biotic components of the environment. Like it can be animal waste, human waste, plant waste, crop residue waste. Okay, so that also categorizes as one of the types of major waste, like biodegradable waste. Okay, and when we say municipal solid waste, a substantial portion of MSW in India is biodegradable. Okay, so that's why I have tweaked the title of the talk. Instead of having purely waste to hydrogen, I said like biomass or waste to hydrogen. So I am here at Department of Hydro and Renewable Energy, IIT Roorkee, since last 5 years. And my main work goes in the area of biomass and bioenergy, and some in the area of waste to energy. But the technologies we work, like gasification, pyrolysis, or chemical looping, they deal with production of hydrogen from these resources also. So coming to global and Indian industry challenges, what are the two challenges? Obviously, we need a lot of energy and then a lot of mass. So world population is increasing, urbanization is increasing, there is a lot of transportation, heating, industrialization is happening. So we need to satisfy the growing energy demand of the world. And then for all of these industries, we need lots of raw materials or auxiliary materials or utilities. I would consider as like say material or matter or mass. So these are actually the not the challenges, but the needs of the world, energy and material. But the real challenge is how do we provide these energy and materials in sustainable way? That means having like very less impact on the environment while satisfying these demands for energy and mass. So when this is a challenge, it's good to see that bigger economies in the world have progressed and like have come forward, have taken the responsibility that okay, we are committing like crime towards the nature through our emissions, through global warming. So we need to set our net zero ambitions. And good to see that US, European Union, China, they have set their ambitious goals by 2060 or sooner, and India is not far behind. India was way behind so far as the industrial revolution was concerned, but so far as contributing to NDC, the nationally determined like contributions towards global climate change, we are very much like in competitive space with other developed economies in the world. So that is 2017. So before that, I'm just showing these two graphs. On left side, you can see the global CO2 emission. This is a slide from 2023, but the percentage-wise numbers are similar. So most of the CO2 emissions, they come from the consumption of energy. When I say energy, it can be in the power industry, like the other industries, transportation, buildings, fuel, all. So this energy sector has a very big contribution towards like global emissions. And then some emissions come from industrial process, agriculture, forestry, and the waste and other. Like this waste includes the municipal solid waste. And if you look at the countries, I think the bigger countries which have set these ambitious targets, they are amongst the leading emitters like China, US, followed by India, Russia, and the rest of the Europe together. So when we have these challenges in front of us, so do we have solutions to it? Yes, of course, there are multiple solutions. And one of the leading solutions is to go for alternative fuels and renewable energy, because most of the emissions are coming from fossil fuels. So the alternative to fossil fuels is renewables. But then there is something called carbon capture utilization and storage, or low carbon or negative emission technology. So this CCUS is a very wonderful thing. Like again, it is not yet commercialized in many parts of the world, including India, because of the cost concerns. Uh, just imagine like if CCU, like capturing carbon dioxide from the atmosphere and then storing it and using it for other purposes becomes very easy and economical, then we don't really need to worry about consumption of fossil fuels, isn't it? So that's why like the CCUS is a very interesting thing, and if it becomes economical and feasible at mass scale, it can reduce the load on renewables or the renewable based policies, and we can continue to use fossil fuels at the same rate. But right now we don't have that carbon CCUS, so we need to go for renewables and alternative fuels in a much faster way. And then another thing is efficiency improvement in the existing technologies. Since we know that we are not going to stop using fossil fuels, but there is always a scope for improvement in efficiency, so that the particulate emissions or some specific greenhouse gases emitted from consumption of fossil fuels get reduced. So those scopes are always there. So in all these solutions, the topic of today, like biomass or waste, I find it to be special because like when we talk about biomass is also a renewable resource. Okay. But when we talk about other renewables like solar, wind, hydro, geothermal, each of these resources can satisfy our energy demand. Biomass or waste is the only thing which can satisfy not just energy but also a lot of material demands. Like we can make lots of materials, biochemicals, composites from biomass or waste, which otherwise are made from fossil fuels. So that's why it is a special, being categorized as a renewable energy resource, but it also can supply a lot of material alternatives to those which are otherwise obtained from plastic, metals, and other fossil sources. So that was about the specialty of biomass. But then other thing about biomass is like it captures and stores atmospheric carbon. Because if you talk about biomass coming from say forestry or industrial sources, forestry or agricultural sources, they are mostly plants and trees, which takes a lot of CO2 while they are growing. And when they are burnt or used for energy purpose, it's actually the same CO2 which goes back into the atmosphere. So because of that biogenic carbon, the carbon emissions, the net carbon emissions for biomass-based technologies comes out to be lower. And also most of this biomass is available in the rural areas. So there is a huge potential for uplifting the rural economy if we come up with the biomass-based technologies. and then there are versatile applications. So with that, but how do we switch to like biomass or renewable? So all those four solutions which I told, how do we move towards that? And the, I think, process towards going from that fossil fuel economy to the renewable economy is called as energy transition. And that's what we keep on talking about these days. So we need energy transition, which is basically like I have shown here, like this black economy to the greener economy. So it's a global energy shift from fossil-based systems to renewable systems. But it is not just the production of energy or the sources of energy that needs a shift. It's the entire framework of energy production and consumption. So when we talk about the entire grid, it will be like energy generation, energy transmission, energy distribution, energy storage. All these aspects need transition or need upliftment. And so far as sources is concerned, it needs a shift from fossil to renewable. Or in terms of sustainable development goals, again, this is another important thing nowadays. If you are writing any funding proposal, or if MTech students or PhD students choose any topic for their research, they need to justify how it satisfies the sustainable development goals listed by United Nations. So goal number 7 is affordable and clean energy. So basically converting unaffordable and unclean energy to affordable and clean energy is also the foundation or one of the fundamental aspects of energy transition. So so far as India is concerned, these three pillars of energy transition, I would see it in the area of power, that is grid, industries, and transportation. And this is where like hydrogen is going to be very important. So when we say about grid decarbonization, obviously it will be based on the power or the fuel mix in the power generation sector. For industrial decarbonization, mainly the hard to abate sectors like cement, steel, chemical, fertilizer, there are several avenues where energy could be provided by renewable resources, as well as material can be provided by energy resources. For example, in steel industry, there is a huge scope for utilization of hydrogen, not only as a source of fuel or energy, but also as a reducing agent. Then in fertilizer industry, we need urea, for which ammonia is one of the very good feedstock, for which again hydrogen is a precursor. Then in chemical industries, for many chemicals, hydrogen can be used as a intermediate. So that's the industrial decarbonization. And in transport transition, there can be transition through different ways. Like we can opt for public transport or some like better ways of living, like to keep yourself fit, like cycling, electric vehicles, hydrogen vehicles, proper urban planning so as to fit public transport system in there and avoid excessive, like say traffic wait time or something like that, which ends up emitting lots of pollution. So these three sectors together contributes to 90% of India's current emissions, like the grid, industries, and the transport. And when these three sectors could be decarbonized in the process of energy transition, it would help us to achieve that net zero goals of India by 2070. Now, while let's look at like when we talk about decarbonization, what like in India, like there are different things which will contribute to decarbonization. Where does hydrogen stand? Okay, so this is a graph from McKinsey report of I think 2024, and at present in the current scenario, we have 160 gigatons of CO2 equivalent in total emissions. And if you want to reduce it, the potential, even under the accelerated scenario where we say that like out of all those four solutions which I mentioned earlier, we can reduce maximum 50% CO2. Okay, and it will need an investment of at least $5 trillion. Okay, so in that 50% reduction, contribution of scaled up green hydrogen is going to be only 4%. Most of it is going to come from renewables, that is around 10%. circularity of materials. Then carbon storage recovery will contribute to 15%. Nature-based solutions like sustainable farming or like plantation of trees, afforestation, all those things will contribute to almost 10% reduction in emissions. Then EV penetration is somewhere at 2%, and then there are others, which includes a lot of things on the planning side, management side, policy side. They can contribute to 8%. So green hydrogen stands here, but among all the chemicals, it's good to see that at least hydrogen is being considered as a significant entity here, which can contribute to decarbonizing India. And it's because of its potential to be used in multiple sectors. So if you look at hydrogen production technology options, mainly from fossil resources, it comes either from coal. From coal, it will be mainly from biomass gasification, the coal gasification. And for natural gas, it's the steam methane reforming of natural gas, which produces most of the hydrogen in the world at present. So for coal and or the fossil fuel based, these are the very well established industrial processes. They are relatively lower cost, and large scale commercial plants are there already. And these plants can be integrated with CCUS options. Because once that mixed gas stream passes through PSA column, like pressure swing adsorption, you get a stream of CO2, which is relatively pure, and that CO2 can be easily captured or can considered for CCUS option for capturing and storing. But most of the time it is done by amine-based adsorption systems. And then there is a huge potential for like doing combined heat and hydrogen power production. So like we have CHP plants like combined heat and power. Nowadays we talk about heat, hydrogen, and power. In bio and waste resources, there is still a lot of R&D going on. Some lab scale or pilot facilities are still there. So far as waste to energy is concerned, some commercial plants are there in different parts of the world. But so far as waste to hydrogen is concerned, very few have been successful, and most of them have been a failure. That's what we will look today in the next slides, like why those plants failed. Okay. But here for waste or biomass, most of the time the successful options included like anaerobic digestion, like forming methane or biogas, or the fermentation of the waste streams. And the other way to derive hydrogen from like dry waste or dry biomass is thermochemical conversion processes like gasification or pyrolysis. And then we have direct water splitting, where we can do electrolysis and the power required for splitting water can be used from nuclear, solar. Then we have so this electrolysis process is also like now almost, I think, more than 50 years it has been proven. And we have been trying to merge it with the cheaper or cleaner what we say energy options, so that the hydrogen from water becomes a sustainable one. So let's decide. Before, for biomass and waste, let's talk about some numbers. For 1 kg hydrogen, generally we need 12 to 20 kg of biomass. This I'm talking about raw biomass, not the dry biomass. So it may have 10 to 20% of moisture. Then 25 to 35 kg of MSW. These numbers are with respect to India, okay, and 10 to 15 kg of RDF. So it's like one each. So if you have to produce hydrogen from biomass, it will need this much biomass for 1 kg hydrogen. MSW, it will need much more because of the high moisture content and high fraction of inerts in Indian MSW. So inerts won't contribute to any reactions. Then in RDF is a very like say sophisticated or the processed form of MSW, where we take only the combustible fraction of MSW. So it will have a very higher calorific value, even higher than biomass in some cases. So we will need less amount of RDF for 1 kg of hydrogen. And the process typically which I have considered here is a gasification. Okay, so we can gasify biomass, we can gasify MSW, we can gasify RDF. And these are some numbers on the carbon content or the cost. So at present, like I said, for 20, so from biomass to hydrogen, the gross CO2 is around 20 kg. RDF is almost similar to biomass, and MSW is little higher. But if we talk about net CO2, only the CO2 contributed by fossil fuel. So if we compare it against like the steam methane reforming, it's 9 to 12 kg for gray hydrogen, which is the most commonly used in industry, and the cost is cheaper, like 150 to 220 rupees per kg. But for MSW RDF, it's a little higher. Because most like some components of the RDF or MSW will have the fossil carbon, though most of it is biogenic, but some of it will be from paper, plastic, cardboard, which may not be biogenic in nature. But when you use biomass, the net CO2 is lower because of the biogenic carbon. But if you look at the cost, it is still much higher for biomass. Even higher for RDF, because some cost goes into production of RDF from MSW. Okay, that's why for RDF to hydrogen cost is higher. And MSW to hydrogen cost is relatively lower here for India. We are talking about the practical case, mainly because see, MSW is not a better feedstock, it's a poor feedstock. We need more amount of quantity, but CO2 emission is relatively less because of less carbon content. But the cost is less because of the tipping fees. Because when waste MSW in its raw form directly sent to the plant, the supplier gets some money from the collection of waste. And if it is that number is subtracted from this, and that's why this cost is relatively lower. So when we talk about biomass to hydrogen for India, like where do we stand at present? Okay, so India has a huge and distributed residual biomass, like almost 750 million metric tons per year, out of which 230 is surplus, because most of it is used for like say fodder and other usage. There are different types of crop residues, and not everything goes to waste, or not everything ends up being burnt in the field. Okay, so and then we with the under the National Green Hydrogen Mission, which was launched in 2023, there like the mission has expected like at least 5 million metric tons of hydrogen per annum by 2030, and these are the expected outcomes of the mission. But it's a long way to reach there, because 8 lakh crore in total investment is I'm not sure it's feasible in the next 4 years. But so far as the hydrogen definition is concerned, what do we call as green hydrogen? Typically, if the emissions are less than or equal to 2 kg CO2 equivalent per kg hydrogen, we can call it as green hydrogen. So less than 2 kg, what you see here, biomass has the potential, okay, to have net CO2 emissions to be less than 2 kg. But others, like the gray hydrogen or the steam methane reforming, MSW, RDF, they won't fall in the green hydrogen category. Okay, obviously, if we add carbon capture and storage thing like CCS or CCUS, then it becomes blue hydrogen, and it may fall under the category of it will also not fall under the category of green hydrogen, because even after putting those CCUS units, these numbers don't go below 2, and hence the only green hydrogen that we get is either from biomass or from electrolysis, where energy is coming to mostly from renewables. So, but again, with respect to biomass, there are other advantages, like it can come with the CO2 capture. It reduces the other issues of pollution. It can create rural incomes and jobs. Same applies to the waste also. Like India has a huge, like I think more than 60 million tons uh, MSW per year. And if waste could be managed for producing hydrogen or for producing energy, it would create lots of jobs, and it would resolve other problems which otherwise originate because of the mismanagement of that waste. So if when you look at the different types of hydrogen pathways and cost in India, so I have given you two costs: 2025 the current cost, and the projected ones for 2030 as per the National Green Hydrogen Mission cost. So in the gray hydrogen area, it's mainly from steam methane reforming with natural gas. The price is lowest at present, and that's why it's the industrially accepted process. The only factor here to control the price is the scale of economy. So the plant scale is important. Whichever country has huge amount of natural gas, the purified natural gas, they can go for bigger plants of producing hydrogen. Then with the blue hydrogen, when we add CCUS, like 0.7 to $1 gets added further, like 2.8 to $3.5 become the cost per kg. And then the price at which that gas is sold, or the capture rate. How do we what so here CO2, when it is separated or transported and stored, uh, where does it find the market? That will also determine this price for blue hydrogen. Like if the utilization of CO2 is somewhere nearby, it would reduce the cost of shipping and transportation. But if it is somewhere very far, or if there is no use found based on the purity of CO2, which is obtained after separation, then it becomes a challenge for blue hydrogen production. Then green hydrogen, it comes with electrolysis with RE grid. The price is much higher, like almost double. And this price is expected to be 200 to 300. Again, it's not below $2 per kg for sure, even in 2030. And when it comes to RE, renewable energy, there are like so many factors which would contribute to this cost of hydrogen. So what's the tariff? First of all, what's the tariff of renewable energy and the source, whether it is from solar or wind, depending on the location in India. And then what's the capital cost for electrolysis or electrolyzer and efficiency, the plant utilization factor, and the sources of financing. Because when it comes to renewable energy, a lot depends on the subsidies given by the government also. And that will also contribute to the final cost of hydrogen produced by green electrolysis. And suppose if we don't use the grid renewable energy, and we have some standalone renewables or electricity at small scale. So if we have the best case sites in India, the price is relatively lower, but it's still not that significantly lower. The only thing is like the utilization would be high because of the small scale. So far as biomass or waste is concerned, for large scale gasification is a technology which has been tried, but its cost is higher than electrolysis also at present. And the projected cost also comes out to be higher than the electrolysis. And the main challenge here is like as we go on increasing the scale of production of hydrogen from biomass, the availability of feedstock or the cost of feedstock, logistics, the continuous supply chain, those becomes issue. Because most of the feedstocks that we talked about earlier, like what we say, paddy straw or cotton straw, they will be available only once or twice in a year. So they will need a lot of storage if you want to use it for throughout the year. But something like MSW, it can be available throughout the year. But then we have some different challenges there so far as like the segregation and sorting of waste is concerned. Then in biomass, there is a problem of tar. When we do gasification, you may be knowing like biomass is like, let's take example of a piece of wood. If we heat it in absence of oxygen or in some presence of oxygen, we are not burning it. We are not doing combustion. But if we heat it in limited oxygen, it will release the volatiles, and those volatiles will have some gases which condense and some gases which are non-condensable. So these condensable gases are the ones which form tar. And if this tar is not cracked further into the gaseous form or the smaller molecules, they will go and block the nozzles of the engine, or they will just block the pipelines connected to the gasifier for flowing the gas. So that tar reforming and cleanup is a very big challenge in biomass gasification technology. And then scale CO2 crediting. These factors would also account for the cost. For small plants, you may be seeing some research papers coming up recently which report cost as low as 150 rupees per kg, which is like less than $2. But practically speaking, it's not feasible, because they take some assumptions where the waste or feedstock is available to them for free. For example, a owner of a big farm who has a lot of farm, like say 100-acre farm or 200-acre farm, lot of farm crop residues available, then that person need not buy the feedstock. He can process his own feedstock, collect it, produce hydrogen or electricity or gas out of biomass from the gasification. So the logistics would be simple, locally waste available. Capital cost would only be the concern there, which will determine the cost. So there is a huge variation in this cost. It's mainly because of that feedstock context. Like someone gets feedstock for free, someone has to pay for it, someone has to ship, store, and transport, and that changes the whole economics of the process when we talk about producing hydrogen from biomass. Okay, so since we're talking about steam gasification of biomass, let me cover this slide, and then maybe we can take a break of 2 minutes if there are any questions, and then we'll continue further. So this is how the typical gasification process looks like. Like you have biomass coming from different sources. It needs to be pre-treated. When I say pre-treatment, you can either pelletize it, you can densify it in the form of briquettes, or it can be simple drying if the moisture content is high, if we need less moisture. So it can be drying, or it can be particle reduction, shredding. So it involves all sorts of pre-treatment. Nowadays, one of the very common pre-treatment thing is torrefaction, where we try to convert biomass into like charred powder, like where we just get rid of all the moisture and some volatiles, so that we get some charcoal like thing, because then it becomes very easy to mix it with coal and co-fire, or to use the same conveyors as coal conveyors in the power plants. And then that biomass goes to the gasification line, where we have gasification agent. So gasifying agent can be anything which contains oxygen. So it can be air, it can be pure oxygen, it can be steam. Steam H2O, it also has oxygen, and it can be metal oxides also. So any oxygen containing species can be used as a gasifying agent. But so far as if the objective is to produce hydrogen from biomass, the most preferred input or the gasifying agent is steam, because steam helps in shifting the reaction towards hydrogen formation. And once we get the syngas, the next steps are the syngas conditioning or the syngas cleaning. So it involves cyclone and scrubber. So you have cyclone and scrubber, and then the filter to remove H2S or CO2 or some particulate matter, fine particulate matters. So all those things, when are removed, the clean gas, the gas which is free of tar, uh, particulates, uh, and H2S, it goes to the water gas shift reaction. So water gas shift reaction is basically to adjust the ratio of CO2 to hydrogen. So this is a reaction where CO gets converted to CO2 or water gets converted to hydrogen, and it's a reversible reaction depending on the catalyst, mostly nickel based catalyst which we use. The reaction can be controlled in such a way that the temperatures where this happens, it's between 150 to 400. So in industries like before 2020, I guess, yeah, there is most of the industries use two shift reactions, low temperature shift and high temperature shift. But nowadays, if we operate somewhere between the temperature range of low and high, we can do this shift reaction in a single reactor with modified catalyst, and that increases the ratio of H2 to CO2. And so the final gas, which contains mainly hydrogen and what CO2. So when it goes to the separation or the pressure swing adsorption PSA unit, so, or the CO2 separator, the CO2 is separated and pure hydrogen is available for storage. Okay, so that's how the overall stream, like overall pipeline of production of hydrogen from steam gasification looks like. One interesting point here I missed is like in gasification, because temperature required is around 700 to 800 degrees Celsius. So there is a lot of requirement of heat. Now, how do we, if we are putting steam into the gasifier, steam cannot be at that high temperature. It will be at maximum 300, 350 degrees Celsius. So how do we achieve those temperatures of more than 600? So in that case, one way is to provide heating from outside the reactor, but then for that we will need some extra fuel, or we will have to use some syngas to provide heat. The other way is, like, since we do the gasification, we can send some oxygen or air along with steam. So when we send oxygen with steam, so it's called oxy-steam gasification, and oxygen will burn some portion of biomass to provide heat, which will be used for gasification within that reactor. So that's why. So when it's, though I mentioned here steam gasification, oxy-steam gasification is a more like economically and technically feasible process, and it would be more yeah, cheaper. We don't need to provide any additional heat. These are some figures from one of the general studies where you can see the composition, the gas composition for steam gasification of biomass. So as we go on increasing the temperature of gasification, you can see the hydrogen mole percentage. It increases from 50 to 60 to 70%. 70% of hydrogen in the final gas is a huge amount, and this 70% hydrogen needs to be separated from CO2 in this separation in PSA unit. And if you look at the tar, as the temperature increases, the tar in the producer gas or the syngas, it will break down into the smaller portions of gas. So actually, the increase in the peaks of these gases, some portion is attributed to the breakdown of this tar into the gaseous form. And then the solid residues, like the char and ash, which is left at the bottom, that also goes on reducing with the increasing temperature. It means some portion for this gaseous products increase is also coming from solids. And if you look at the efficiency of gasification with the temperature, it the higher efficiency is around, like, say, for 10% moisture, it's around 720, but for 20% moisture, it's around 650. So depending on, like, so how moist the biomass is. So if biomass has higher moisture, we would get better efficiency at lower temperature. But if it has, like, say, 10% moisture, which is ideal most of the time, we will have a higher efficiency around 720, 725 degrees Celsius. And if we go on increasing temperature beyond that, it will reduce the gasification efficiency. The gasification efficiency is calculated based on energy output by energy input. And if you look at this gas composition, let's focus at 600 to 800. So in this gas composition, CO2 has no contribution to energy. CO, methane, and hydrogen. So CO, methane, hydrogen, and tar. This, but tar won't be collected with the gas, so it's separated out. So CH4, CO, and hydrogen. These three components gives us energy. So the energy of this by the total energy of the biomass. That's how we calculate the gasification efficiency. Okay, so let me just take a break here of 2 minutes and ask like if you have any questions or queries. Hello.
Yes, sir. Yes, sir.
Yeah, I'm audible.
Yes, sir. Yes, sir. Sir,
Okay.
as
if,
we are,
Hello.
yeah, please.
hello.
Is it
Yeah.
audible,
So
sir?
if there are
Okay.
any questions, please feel free to ask by unmuting, or you can write in the chat also.
Hello. Is it
Okay,
audible,
sir.
sir?
I have one
Yes.
question.
Yes, please.
In the carbon storage system that you mentioned earlier, CCUS
Yes.
system,
Mhm.
carbon capture uses storage system, I guess.
Yes.
So it was stated that the carbon is stored and it is used for the different applications.
Yes.
So may I know what are the applications that this stored carbon is used for?
So when we capture carbon, let's say we mostly capture CO2. So depending on the purity of CO2 captured, the applications can be decided. So if we are capturing CO2 in the gaseous form, and if we are storing it in the cylinders, it can be used for fire extinguishers. It can be used as a dry ice. The 100% pure CO2 is also called as dry ice. Now, if we have some impurities in CO2 and we are just storing it in like normal G-size cylinder, uh, so it can be used for making urea. So urea reaction is CO2 plus ammonia. So carbon dioxide is one component, ammonia is second component. If we react these two together, we get urea, and urea is a very good fertilizer. So that's one more use of CO2. So depending on the purity of CO2 that we have obtained after capturing, we can decide the application. So most common use is in the this refrigeration systems also. Yes. So that covers the CCUS part, the utilization part. And many technologies we just talk about CCS part, carbon capture and storage. There, like we can even consider like let's take example of oil well. So when we take oil from the oil well, now that oil well is empty, so CO2 can be injected into that oil well, and these oil wells are very deep into the ground. Similarly, there are aquifers underground. In those aquifers, CO2 can be injected and it can be sealed and stored. That also gives us CO2 storage. So that CO2 will not be available for use for a long time, but we have done the capture and storage. Capturing and storing CO2 means just taking CO2 from atmosphere, which would go into the gaseous form, convert it into either compressed gas, liquid, or solid form, and put it anywhere except for the atmosphere. Yes. Do we have any more?
Okay, sir. Thank you so much.
Hello. Good
Yes.
evening, sir. Is it audible?
Yes.
I wanted to ask, yeah, that you told about the three temperature, 600 to 900 degrees
Nine.
Celsius. So you told that in first case, the higher the temperature, higher the hydrogen yield. And in otherwise, like second graph, you showed that energy efficiency is higher in case of lower temperature. So I wanted to ask that which is economical, which process is economical for the
No, so it depends on the purpose and the biomass that we have. See, if for higher moisture, we are getting more hydrogen, and if our desired product is hydrogen, then that is better for us. But if our desired product is energy, if we want to run IC engine on this gas coming out from biomass, then we don't need hydrogen. We just need a energy rich gas. Now this gas has methane, hydrogen, and CO. If you look at the calorific value, hydrogen would have the lower calorific value than CO as well as methane. Methane has much higher calorific value. तो अगर हाइड्रोजन का परसेंटेज कम है हायर टेम्परेचर पे, पर सीओ और मीथेन का परसेंटेज ज्यादा है, तो नेट एनर्जी कंटेंट गैस का ज्यादा है. तो अगर पावर जनरेशन के हिसाब से, गैसिफिकेशन के हिसाब से उसकी एफिशिएंसी फिर ज्यादा होगी. So it depends. But if our objective is getting hydrogen, then we should stop at the lower temperature. If our biomass has higher moisture, we can get higher hydrogen at lower temperature. So it solely depends on the purpose. Also, like if 20%, if higher moisture is there, it means it will save us drying cost also. बायोमास को ड्राई नहीं करना पड़ेगा 10% मॉइस्चर तक, 20% पे वी कैन फिट, सो इट विल सेव अस some cost on operating cost also.
Okay, very thank you, sir. I got the point. Like,
If there are no questions, I'll just take 1 minute break and I'll join.
Yeah, sir. Yes, sir.
Yeah, I'll just drink water.
Okay, no problem.
Hello. So can I have one question?
Just a minute, ma'am.
Hello, am I audible?
Yes, sir.
Yes, sir. So I have one question, like one doubt.
Yes, please.
So in the case of concentration, like because I'm working in the field of membrane distillation, so if the process is for concentration of anything, like for waste stream, we want to concentrate the stream so that we can recover some valuable products. So in that case, can we use that water that is available for drying out? Can we use that for producing hydrogen efficiently?
You mean the water which we obtained from drying of feedstock? Can we use that water for hydrogen production?
Yes, like for any process, wherever there is concentration kind of thing is involved. So can we additionally install one plant where hydrogen can be generated by drying out that water, and like we will get both the things, hydrogen as well as concentration.
Yes, yeah, but unless we need hydrogen in that plant, there's no need for having hydrogen generation setup. Like if you are separating, like if you while concentrating something, if you are separating water out of it, from that water, hydrogen can be produced. But if it's not pure water, it's difficult to produce hydrogen from that, because we need like pure water, and then we usually add electrolytes to it. for electrolysis to take place. So I'm not sure if I understood the question correctly, but if you are thinking of producing hydrogen from water evaporated during drying, it is
Yes.
possible. But
Yes.
water obtained during concentrating something, that water may have
Mhm.
other impurities, that is not feasible. But if you are doing boiling and then water is vaporizing and then it can be condensed and it can be used.
Okay, sir. That
Uh,
satisfies
yeah. But
the question.
unless
Thank you.
there is a need for hydrogen they at the same plant, it won't make much sense to produce hydrogen from that evaporated and condensed water.
So because
Okay, so
anyways we are using energy for evaporation, so at the same time we can get the hydrogen as well, right?
no, because to get hydrogen we will need to put some more energy, some more
Additional. Yes,
electricity.
sir. Yes,
Yeah,
sir.
yeah. So that's let me share the screen. So now I'll just finish the remaining PPT and then we can have more questions.
Yes, sir. Yes.
Okay. So it's again maybe 10 more minutes and then we will have 10-15 minutes more for
Yes,
question
sir.
answer.
Yes. Yeah. Yes.
So this is the technology status for so far as biomass to hydrogen is concerned. Out of most of the technologies, it's a gasification plus water gas shift plus pressure swing adsorption. That is the separation technology between CO2 and hydrogen. If you look at like TRL level, technology readiness level, it is still at pilot and demo scale, 5 to 7, because we call something as commercialized when TRL 9 is reached, right? So we don't have any technology at 8 or 9 also. If you read some like a newspaper, magazine, or some research paper, you may find some people commit like revealing that they have TRL 9 level technology, but there's no point in believing that, because if it is at TRL 9, then we should have this biomass to hydrogen or waste to hydrogen successful commercial plant in India, but we don't have even a single plant at commercial level. I will talk about the plant, the India's first plant, which was about to come in Pune only, and it failed terribly. It did not even start operations. Okay. So the gasification, the key challenges this I have discussed. Some pilots that I told they are with Indian Oil and IISc, and the yield is around 80 to 120 kg hydrogen per ton of biomass. So it's like the ratio of 0.1. Okay, so like 100 kg biomass will give us 1 kg hydrogen. Supercritical water gasification, again, it's at very early stage, but it needs high pressure, because when we use something at supercritical level, so high pressure material increases the cost of reactor substantially. Okay, and it is also still at research level. And about pyrolysis and reforming or dark fermentation biological processes, there the yields are very low, and they are also at lab scale. They give even lower yield of hydrogen compared to the other processes. So the challenges overall here with respect to biomass and also with respect to waste is the feedstock supply and logistics, because of the seasonal gaps, and there is a high delivery cost, high storage cost, transportation cost. So these are some recommendations given for overcoming these challenges. So we can either have FPO contracts where like the bigger farms can store the biomass, and or the FPOs can store the biomass collecting from the smaller farmers, or we can produce pellets and torrefy the biomass so that it can be stored for a longer time. It can be shipped at lower cost for longer distances. Then the quality variability or the heterogeneity. Biomass or waste is highly heterogeneous. For example, even in the Pune Municipal Corporation, if you take the example of landfill, the waste coming every day on that landfill won't be similar in composition. Every day, the composition of waste would be varying. So we cannot design a plant over a very small range of composition. Okay, and that composition of waste or biomass will depend on the season, because with the season and time of the year, people's habits changes. So the amount of waste as well as the quality of waste generated also changes. Okay, so that quality variable is always there. And tar and cleanup thing, I have told earlier, CO2 capture is there. Reliability and economics, main thing, okay, which is stopping India from going into biomass or waste to hydrogen is the economics and offtake. So this LCOH is like the life cycle also levelized cost of hydrogen, and it is not the cost of hydrogen produced by one operation, but it's the average cost of hydrogen over the entire project lifeline. And there, this cost never comes to be less than $2 per kg, which is making it a very challenging task. So I was talking about Pune's case studies. So India's first waste to hydrogen plant was to be set up in Pune, and this came in February 2023. Okay, the cost of project was 430 crore, and it was not just Pune Municipal Corporation plant, but with a company called the Green Billions Limited. It's an Indian public sector company, and they had this 30-year long agreement, and objective was to process 350 tons of solid garbage every day and produce 10-ton hydrogen per day. Okay, if you remember the numbers which I showed you earlier, 1 किलो हाइड्रोजन के लिए 35 kg MSW लगता था ना, तो वही रेशियो है यहाँ पर भी. 350 टन MSW पर डे प्रोसेस करेंगे तो 10 टन हाइड्रोजन दिन का बन सकता है. And the technology which was employed was plasma gasification. But when all these cost estimation calculations were done, there were lots of like flaws in it, and it was found that finally the hydrogen जो बनेगा, it was costing around $6 to $8 per kg. And $6 मतलब आज के लिए 550 रुपए per kg or 600-700 रुपए per kilo hydrogen. Nobody would be buying it. So the project is not at all economically feasible, and because of this reason, Pune Municipal Corporation withdraw its 90 crore funding. 430 crore का जो था प्रोजेक्ट, उसमें करीब आधी फंडिंग तो इन दोनों की थी, और जो इंडिया का नेशनल ग्रीन हाइड्रोजन मिशन था, इन्होंने भी जो 260 करोड़ की सब्सिडी दी थी वो भी विड्रॉ कर ली. So now what went wrong here actually? So Pune is like it's not a metro city, but it's like the tier 1 cities only, between tier 1 and tier 2 cities of India, and the MSW is huge in a huge amount, and segregation is also possible in a city like Pune, Bangalore, Hyderabad. Okay, but then plasma gasification plants for waste MSW or waste to hydrogen, they have failed in the best parts of the world also. So there's no surprise like it failed in Pune. I'll tell you some examples. In UK, there's a Tees Valley plasma gasification project. This is the aerial view. You can see it's like it's spread over like huge amount of area, and it was initiated by Air Products. Air Products is a very like one of the biggest gas supplying companies in the world, and it was $1 billion project. इससे 3 गुना बड़ा था, 1000 ton per MSW and producing 50 megawatt electricity. Okay, they were not even producing hydrogen, they were producing electricity. So they just need the gas from plasma gasification from MSW, but they had issues with feedstock variability, because when you ask for such big amount of feedstock on a daily basis, and if it is varying substantially in moisture content or in the biodegradable or organic or inorganic content, there will be a lot of technical issues in handling and processing that feedstock, and the reactor won't give the same performance that we predicted using small lab scale reactors. Because when we do research in our labs or even on simulations, we take a very refined, very clear feedstock. When I do research on municipal solid waste in my lab, I just take paper, plastic, cardboard, and then we really wash it, dry it in sun or oven, then shred it into the powder, and then put that feedstock in the gasifier or pyrolysis, and then we do the measurements. But in reality, it's not like that. In the real sample would be contaminated with a lot of dust, soil, water, and it will be randomly mixed with lots of metals and all. And if I try to put that feedstock in my reactor gets choked. Okay, so I think those technical issues show up when we try to do something at pilot scale or at industrial scale. So there are a lot of operational challenges in this plant also, and they realize that to overcome those challenges, they will need $1 billion more. Now the entire project was $1 billion, and if they want ask $1 billion more, they would never go for it. So and they wanted to double down. They wanted to have this 250 megawatt plants. So since their first valley did not work, the second valley construction work also never completed, and ultimately Air Products, they stopped their plasma gasification waste to energy plants, and this was way back 10 years back in 2016. And this Air Products, they said they will not work in the waste to energy sector. Okay, they will continue to work in the gas supplying, where they are doing very good, and they did not invest any more money in the waste to energy. Similarly, another plant was in Canada by Plasco Energy Plasma Gasification Project. Now, this Plasco Energy is one of the world-renowned plasma technology provider. They themselves have their own technology, and it was in 2007. Their project cost was 71 million Canadian dollar. It was in Ottawa, a very sophisticated technology. As you can see, it's very clean, nicely maintained. And they operated this for more than 15-20 years. It is still operational on 100 tons per day for MSW. But during these 15 years also, many times they faced downtime, like where the things get choked, the reactors, the pipelines got choked, and they had to halt the operation. Now, this area is not a big area. Now, and if some plant needs 100 tons of feedstock per day, they will have to tie up with some municipality or someone who will be supplying that much feedstock every day. Now, if there is some downtime and the plant gets shut down for 8 days or 10 days, then 800 tons per day waste, where will it lie? They will need to create some extra storage here additionally, and those things lead to huge cost. Also, because this plasma reactor operates at like say more than 1000 degrees Celsius, 1200 degrees Celsius, it needs a lot of cooling, and there was a huge water requirement. And this area township had a lot of issues with water, so the mayor did not allow huge water usage in those plants. And when they tried to scale it up to 3 times, they failed to get finance, because at 100 tons per day itself, they could not show the plant is profitable. And finally, the company went bankrupt in 2015. But now, what they are doing, they did not close, but since they have this proven technology, according to them, they shifted their business model from owning and operating to selling or licensing their technology. Now, tell me, like, whether it makes sense, like the company, which is itself a technology provider, if they themselves cannot run the plant profitably in their own country, when some other country buys the technology and tries to implement it, it will not work. The same happened with the waste to energy plants, the incineration based waste to energy plants in India. The first plant came to Delhi in Okla Timarpur, and it failed because it was not with respect to the waste in India, and the technology needed highly segregated amount of waste. So what now? if waste to energy or waste to hydrogen is not going to work, should we stop it, or is there any other way? So the examples that we saw, including Pune, UK, or Canada, they are all about plasma gasification or the gasification of MSW. But there are other ways to generate green hydrogen from biomass or waste. One way is using waste plastics. Okay, so when we say MSW or RDF, it includes a lot of things: paper, plastic, cardboard, food materials, stone, glass, rubber. Okay, and with this heterogeneity, it becomes very difficult. But plastic is a very good feedstock. The most common plastic being polythene, polyethylene, polypropylene. इनका फॉर्मूला क्या होता है? CnH2n या CnH2n+2. So it's basically hydrocarbon. बायोमास में तो CHNSO 5 होते हैं और उसमें मेजर होता है CHO, कार्बन हाइड्रोजन ऑक्सीजन. सो इट बिकम्स वेरी डिफिकल्ट टू गेट अ हाइड्रोकार्बन रिच फ्यूल. बट प्लास्टिक तो प्योर हाइड्रोकार्बन है, तो उससे से ज्यादा हाइड्रोजन इजीली मिल सकता है, ऑक्सीजन ही नहीं है उसमें. सो बट देन collecting and then plastics, if it can be collected and segregated easily, they are not very heterogeneous feedstock compared to MSW, and they are very good feedstock for pyrolysis, क्योंकि pyrolysis से प्लास्टिक का तेल ऑयल आराम से बन सकता है. And because plastics don't have oxygen, we would get bio oil with a very good quality, which will not have much oxygen in it. And then that bio oil can be reformed to hydrogen, or if we do fast pyrolysis, we can get syngas, and if we reform that syngas, we can get hydrogen. Okay, so that's the technology. But if you look at different countries, like Japan में एक hotel है, hydrogen hotel by Kawasaki. It's very famous, but the size which they have gone, it's not beyond a pilot scale. So this 75 kg per day, less than 200 kg per day. Okay, and where you are seeing tons of hydrogen per day, like 2 tons, 2.7 tons, or 800 tons hydrogen per day. These are all planned. They are either at design stage or announced. They are not yet into the practice. The one which are already in practice, they are very small plants of like say less than 100 kg hydrogen per day. So less 100 kg hydrogen per day means if you divide it by 24, it will be just 4 kg hydrogen per hour. So that is possible even in a lab scale production also. And this is the one biggest plant which is planned at present. It's for 11,000 tons per day waste, giving 800 tons. It's in Egypt by Hydrogen Industries Hub. But let's see what happens to this plant. But one key thing to know from here is if we have a segregated waste, we can produce hydrogen. Other thing is biogas to hydrogen. Again, in the like few hundred kg per day size, we have some plants coming on biogas to hydrogen. So if we have only the biogenic waste, like say the waste from dairy plants, the poultry plants, or the food waste, kitchen waste coming from hostels or big universities or big townships, they are a very good feedstock for anaerobic digestion, and we can produce biogas from it. Biogas is basically biomethane. And then if we do the reforming of that methane or cracking of that methane, we can get hydrogen. So in India, we have a couple of such plants, which, but again, they are at very lab scale or pilot scale, producing only 5 to 10 kg per day. Somewhere in Australia, we have 100 kg. Again, it's a demo. And in Korea, we have 200 kg per day. Again, it's a demonstration. There's no commercial plant as such, even on biogas to hydrogen plant. But the challenges and issues are relatively less compared to a segregated feedstock and the biogas to hydrogen. So instead of going for direct MSW plant, I think we should go for the segregated waste component, or like biogas is also for food waste or animal waste. So it's like a very clear specific waste. It's not highly heterogeneous. So something like this can be used for producing green hydrogen. So I think coming to the last slide, India's biomass and MSW potential as well as the national.
Sir, you are not audible.
Hello.
Yes, sir.
Okay.
Yeah.
Okay. And to start with, we don't need so many plants or a big capacity plants. What we need is just bankable. When I say bankable, means very thoroughly tested, technologically tested, 3 to 5 regional pilots of 25 to 100 tons per day with CO2 capture, reliable cleanup, and CO2 use. And if those work fine, then we can go for commercializing it at a bigger scale. But we should not be buying technology directly from foreign countries and putting it in India uh, without doing our own pilot scale trials for our own feedstock. And then with respect to biomass and MSW, there is a potential for rural jobs, CO2 credits, along with byproducts. And if we take all these things into account, it will help to increase the financial viability of those plants. And so far as market is concerned, I would rank it like this. First, it should come if we can use hydrogen as a chemical or as a feedstock for making some other chemical or some other higher market value product, we should address that. Second comes to the fuel. We can use hydrogen for fuel in transportation sector or in the steel industry or in refineries. And last comes the power. It makes no sense to produce hydrogen for power generation. Like if we talk about electrolysis, we are using electricity to produce hydrogen, and then again using that hydrogen to get electricity doesn't make sense. Similarly, even if we are producing hydrogen from biomass or waste, using that hydrogen to produce electricity won't make sense because from waste or hydrogen we can just produce syngas and get power out of it. Okay, so hydrogen should be used mainly for chemicals and fuel. So which means the earlier use would be in the refineries, fertilizers, steel industry, followed by transportation sector. So thank you so much. I'll stop here, and then if there are any questions, let's take it. Yeah. Am I audible?
Sir, just a minute. Because of some technical error, I could not use. Just a minute. So here is something technical issue with our system.
Okay.
I have one question. Sir,
Yes.
I have seen, is it audible, sir?
Yes.
Yeah. Sir, nowadays I have seen most of the research paper that microalgae or algae is going to be used as a biomass or feedstock for the generation of the biohydrogen or hydrogen. So
Yes.
I want to ask you, how much quantity, exactly quantity it will require of feedstock to produce the 1 kg of hydrogen. As you have mentioned that 35 kg MSW it will be required for the generation of 1 kg. Is this is the same for the microalgae also? Because
It's the
the
same for microalgae if it is the dry microalgae.
okay.
But to grow that much, to grow 1 kg algae, you will need a huge water pond.
Okay.
And a lot of nutrients and CO2 will go into growing that much algae. So seeing algae as a source for hydrogen doesn't make sense commercially. I would recommend using microalgae to get some metabolites which can act as a active pharmaceutical ingredients like APIs या कुछ metabolites या कुछ chemical उससे enzymes कुछ निकाले तो I think that will have more market value. और वो निकालने के बाद अलगी का अगर कुछ बायोमास बच जाता है जिससे कुछ और नहीं निकल सकता है उसको फिर जलाओ या हाइड्रोजन निकालो उससे दैट्स फाइन.
और सर देखो अभी जो माइक्रोअल्गी लैब स्केल ही हम यूज कर रहे हैं वो कब तक हम कमर्शियलाइज कर सकते हैं? इज देयर इज एनी चांस ऑफ कमर्शियलाइजेशन?
मतलब like algae or like say dark fermentation I don't see it क्योंकि अभी हमारे पास पराली इतना है, कॉटन स्टॉक इतना है, MSW रोज का है, राइस इंडस्ट्री जैसे राइस इंडस्ट्री में राइस हस्क रोज मिलता है तो उसका तो टेक्नोलॉजी अभी कमर्शियल हो गया है. गैसिफिकेशन से लोग बिजली बनाते हैं, स्टीम बनाते हैं और उसी राइस मिल में यूज कर लेते हैं. ओके बट उससे बेटर जो हमारे पास अलग अलग फीड स्टॉक है उसको ही हमें लाइक वी आर नॉट एबल टू डील विद इट. सो दिस अलगी इट विल टेक लॉन्ग टाइम बिकॉज अलगी हमें बायोमास से बहुत कम क्वांटिटी मिलता है.
करेक्ट है सर.
या so it's good for research at present but to see it commercially I think it will take long time. Before that this biomass and waste will find a solution for sure. वैसे माइक्रोबियल फ्यूल सेल नाम की एक कॉन्सेप्ट थी तो माइक्रोबियल फ्यूल सेल में लोग वेस्ट वाटर से हाइड्रोजन बना रहे या बिजली बना रहे बट इट्स वेरी स्मॉल अमाउंट मिली वोल्ट में बनता है. तो वो अगर एक घर के लिए बिजली बनाना है तो बहुत सारा ह्यूज स्टैक लगाना पड़ेगा माइक्रोवेव फ्यूल सेल का. तो इट्स नॉट लाइक द कंसेप्ट इज लाइक बैड और इट्स गुड साइंटिफिकली बट इफ यू टॉक अबाउट कमर्शियली इट्स नॉट feasible.
Okay. Sorry to all the participants. Can you please text your message or question onto the text box?
Yeah, I think
Just
someone
minute. I will try. I will try to make it is allowed from my mobile. Just a minute. Now all can ask. Dr. Mohit Bohre wants to ask something.
I think okay, so I think I can share the PDF like the of my PPT with you if they want. They can have it.
Yeah,
and
yes.
I think this session was it recorded?
Yes, sir. Yes, sir. It is recorded.
Okay. So you have the recorded session also if you want to refer to it.
Yes,
and I will share the presentation also.
Okay. Thank
Okay,
you,
then so it was nice to like I couldn't see anyone, but I could read at least everyone's names. But good to be here and share my insights with all the participants. And thank you, Dr. Jathar and
Yes,
Army
sir.
Institute of Technology, Pune, for hosting this and for inviting me. So good night, and I'll share the PDF file of presentation with Dr.
Yeah,
Jathar.
you can share with me, sir.
Okay.
I will mail them. Yeah. Thanks a lot, sir, for your presentation. It was a nice and interactive session, sir.
Thank you.
Yeah. Thanks a lot.